understand the physics of the theory of the elementary particles, and then we are going to use some algorithms to do predictions using the standard model and beyond the standard model. So the content of this lecture are 6 lectures in that we are going to present different topics. For example, in the first topic we need to do a review of the special relativity, and specifically one topic that is related to that is the relativistic kinematic variables. So this is important because we know that in collider and particle colliders, we have collisions between particles, elementary particles like protons, ions, leptons, and that collisions occur at high energy scales. So the physics that study that high energy scales is special relativity. So we are going to do some introduction to special relativity and study and derive some equations related to relativistic kinematic variables. And that relativistic kinematic variables we are going to implement in Python in advanced uh, lectures. So for the second lecture, we have here we are going to learn some general aspects using Python of numerical integration. We are going to show different algorithms that are very popular to do that approximation of an simple integral. And at the final of that part of the lecture, I am going to present the most important numerical integration that the algorithm based in generation of events using Carlo. We are going to learn what is the Monte Carlo method. So this is important, understand that part of the lecture. And as usual, in talks related to particle physics, is necessary to introduce some aspects of standard model of particle physics and beyond the standard model of particle physics. But as a comment related to beyond the standard model of particle physics, we are going to study from an introduction to two models that are the Z prime leptophilic model and the 331 models, that are models that I study with collaborators in a paper, and our objective is reproduce the results of that paper using for that we need to understand particle physics, the standard model, and beyond. For the second lecture, here is an introduction to the Monte Carlo event generators, and we are going to learn that topics, that concepts that we call events. Events is an important definition that we need to understand in collider physics. So we are going to learn what means events at parton level, hadronic level, and detector level. And after that, we are going to use the first package, fine rules. That is a package that works inside of Mathematica Wolfram. So it's necessary to understand the lecture number 2 because we need to interpret the Lagrangians for the objective for implement in package like fine rules. In fine rules, we are going to implement that Lagrangians, and we are going to generate Python files that MATLAB use to do the calculation. So this is the content of the lecture number 3. And for the lecture number 4, we are going to use MATLAB from advanced features. So here we are going to learn generate events, parton level, hadronic level, and detector level. It's important to say that MATLAB for default, that generate events in Parton level. Parton means that we only have quarks and gluons, but we know that quarks and gluons are not free particles, so we need another complementary package that we can install using MatGraph, that is Pythia. Pythia use that partons and produce a physical effect that is the hadronization. So this is events at a hadronic level, and then we need to put detector effects using another package that we can install using MatGraph, that is Delphes. So this is a full simulation to generate and understand the distribution that we are going to study. And in the 5th and 6th lecture, I am going to present a script that I write in that we can use MatGraph to scan beyond the standard model parameters. We are going to generate a table in that appear the cross section, the value of the cross section for different parameters that we can find inside of the beyond the standard models. And at the final of the lectures of this week, we are going to analyze the events that were generated in the lecture number 4, but that events are in detector level. So we are going to analyze that events in a configuration different from the LHC, that is click. Click is a linear collider, compact linear collider. We are going to use that configuration collider to analyze using Python that set of events. So this is the content of the lecture and the biography that we are going to use today. This is the biography. The two first papers are very important because are test lectures from two research, that is Tao Han and Matthew Thwars, that are papers related to collider physics. And to understand some from an introductory part, the numerical analysis in that we can solve equations, differential equations, integral equations, etc. Numerical stochastic calculus. We can see that books, that is Timothy Sauer numerical analysis. And that paper, the following paper, is the paper that we are going to reproduce the result, searching for a electrophilic Z prime and the 331 symmetry using click. That paper, we are going to find the best region in click in the compact linear collider, in that we can find a new Z prime from the electrophilic model and from the 331 symmetry with right-handed neutrinos. So this is we are going to reproduce the results of that paper. And finally, the research related to collider physics, specifically in simulations. We use deep learning algorithms, but it's important to maintain that alternative bibliography, that is Jason Brownlee book, that is deep learning with Python, develop deep learning models on Tiano, TensorFlow, and Keras, that are a library that we can install in Python. So the events today are analyzed using deep learning algorithms. We start to the first lecture, that is the special relativity and kinematic variables. So I separate these lectures in 3 parts. The first part is important because we need to understand some concepts that are necessary to this week. The second part, my work is motivate the study of special relativity and relativistic kinematics, because I say that we know in particle colliders the collisions occur at high energy scale, so it's necessary to understand some concepts related to special relativity. And finally, we are going to do calculations from mathematics derive some kinematic variables that we are going to implement in our algorithms. The 5 or 6 lectures. So this is the content, and we start with the first um, part of the first lecture, that is the terminology of in collider physics. So it is necessary solve, define some concepts related to collider physics, and to do that, we need to solve 3 questions. So the first question is obviously what is a particle collider. Second question is what means event. That word is important. Event in particle collider. And finally, with that 2 questions, we need to solve the last question, that is what is a Monte Carlo event generator. So we start with the first question. What is a particle collider? Here we put this definition of a particle collider. We know that a particle collider is a machine that uses strong electromagnetic fields to accelerate subatomic particles. But that part of the definition is the definition of a particle accelerator. So we need to collide that particles, and the particle accelerator transform now as a collider, a particle collider, and the collisions occurring at strategic points. This is important. These strategic points for us, from an experimental point of view, we call that strategic point as detectors. We put detectors around the collision points and do and perform particle physics experiments. We analyze the results of the collisions. So this is a particle collider, and in a general form exist 2 types of colliders. For example, in this slide we can see a linear collider that is a future collider. This is the International Linear Collider that use 2 beams of electron positrons, and the strategic points appear here. This the collisions occur here, and we put here the detectors that study the collisions between leptons. Okay. So this is a linear collider. Obviously, the the particles follow a straight path. So this is a linear collider basically. We have here the most famous particle collider, that is the LHC. The LHC is a circular collider, that is other type of colliders. We have 4 in the case of the LHC. We have 4 strategic points of collisions that we call experiments. We have the CMS, LHCb, Atlas, and Alice. Each one of these strategic points has different objectives to study the result of the collisions. So this is a circular collider. We have a linear collider and a circular collider. So with that we can define what means event particle collider. This is a word that is important because here we put the definition. An event is the result of a specific interaction. So for example, in this video, imagine that we are inside of the Atlas detector, and that 2 points are beams of protons. So we have before the collision, we only have 2 types of particles that are protons, and before the collisions, during the collisions, occur the effects of quantum field theory, the quantum mechanics, and appear from the vacuum another particles that are different from the initial particles. So we have a large set of new particles appear after the collision. So our work is analyze the result of the collisions, and each one of these new particles we call an event. For example, we can find here for example, we can have here two pairs of electron positron pair, and we call that a event of two leptons. So a event can be any result of the interactions. For example, this is one of the most popular distributions that we can find in collider physics papers. This is the paper, this is the result published by Atlas collaboration in that confirm the existence of a new scalar compatible with the standard model Higgs boson. And this is a distribution of events versus invariant mass. Here appear invariant mass of two photons. Invariant mass is a kinematic variables that we are going to derive using special relativity. So this is a motivation to study special relativity, because we need to understand and do a correct interpretation of the distributions like that. In the y-axis, we have the number of events that I am going to clarify using my equations. And for example, in this case, events in this case are the production of two photons. So events is the result of the collisions. For example, in Atlas we have proton-proton collisions and produce an Higgs boson, and that boson via a loop final state is two photons. So or even in this case are two pairs of photons. So that with that we define the terminology necessary to understand the 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 topics related to collider particle physics from a simulation point of view. Now we start some motivations to study special relativity exist. Now we are going to show following. You can see the equation, right? So it's important to see why need motivate the study of special relativity. First of all, the detectors detect only two things, basically. A very general point of view, detect energy and the direction of the particles that we can quantify via linear momentum. So that two quantities are important and has part of special relativity. So it's important. This is the first motivation. We need to understand special relativity because we need to understand and interpret what means energy and linear momentum from a point of view of general special relativity. This is the first motivation to study. The second motivation is obviously that equation that is very important. That is the E squared equal to m squared plus b squared. This is the Einstein equation for in our interest for a. Okay. So as I say, This is the Einstein equation that we can use to identify particles. So we are going to see this in another lectures. Exist other motivations. For example, imagine an arbitrary transversal code of a detector that are made of only two layers, the first layer and the second layer. This second layer is a electromagnetic calorimeter, in that if we have a charged particle like was producing here, imagine the travel of that particle, that is an electron traveling, and the first layer confirms that that particle is electric charged particle because produce a curve side of the electromagnetic fields. And when this particle is inside of the second layer, produce a curious effect during this travel that emits photons, right? Emit photons. That effect is known as electromagnetic shower. So we can interpret that electromagnetic shower using the following arbitrary numbers. For example, imagine that the electron has the energy of 28 GeV, for example, and was produced 8 photons. So we have, for example, the photon number 1 has 4.5 GeV, and the photon number 2 has 4.5 GeV. The electron number 3 has 3.5 GeV. The photon, sorry, our photon, electron. The photon number 4 has 2.5 GeV. The photon number 5 has 3 GeV. 6 photon has 5 GeV. And the 7 and the 8 photon has 4 and 1 GeV. So, as I say, a detector detects only energy and the direction of the particles that we can quantify using linear momentum. So we have a set of data that, as a spoiler, we can simulate that data, and we can represent that distribution. For example, we can has in the y-axis number of events, n, number of photons, and in the x-axis we have, for example, energy of the photons. Okay, so for example, we can divide this in 1, 2, 3, 4, 5, and 6. This is EEV. And for example, we count the number of events. Is only a number that we count events, right? Events, y events, photons. So for example, we have photons between 0 and 1. We don't have, but we have only one photon, that is the number 8 photon. We have only photon between 1 and 2. So only one photon appear here. And we have only one photon between 2 and 3 GeV. That is the photon number 4. So we only have, again, only one photon. And between 3 and 4, we can see that we have the photon number 3 and the photon number 5. So we have only 2 photons. So we have 2 photons here. And we have photons between 4 and 5. Yes, we have 3 photons. We have the photon number 1, and then the photon number 2, and yes, the photon number 7. So we have 3 photons. Okay, and we have photons between 5 and 6. We have only the 6th photon. That is only 1 photon. So we create a distribution that we call that distribution a histogram, and our work is analyze the events that occur inside of the detectors via histograms. So this is another motivation to study energy and momentum from a point of view of the special relativity. So with that, we can start this study of special relativity. For example, we start with the study of a 4 vector that is important. A 4 vector in some books is represent, for example, A as arbitrary 4 vector. 4 vector is like a vector that has 4 components, because it's an element that has part of a extent dimension of the 3 dimension that is the Minkowski space. So A can be we can write the 4 vector as A1, A0, A1, A2, and 3. That is what, in the case what we have new, that side we call that as a contravariant 4 vector. And when we have down that mu down part, we call that a covariant 4 vector. So exist different 4 vectors that we can study in special relativity, but for collider physics the most important is the 4 momentum. 4 momentum that we can define as P. P is equal to P0, P1, 2, 3 if we call a contravariant, or P0, P1, P2 if we call a covariant for momentum. P0 here is the energy of the particle, and each part, P1, P2, P3, are the 3 components of the linear momentum. So P equal to energy and linear momentum. So here appear the most important variables in relativistic kinematics. So for example, if we do the exist again the scalar product between 4 vectors that we can define as in that form, or P squared, and is equal to P. And when we have the, for example, here appear a propriety, Pi is equal to minus Pi. So when we have I in the downside, on the upper side, we increment a minus sign. That so that E minus P. So the result of that calculation is basically E squared is element to element minus P squared. And from the Einstein equation, we know that this is equal to mass squared. So p squared is equal to m squared. That equation we are going to use to derive some of the relativistic quantities that we are going to use and implement in our algorithm. So let me see. Another thing that is important to derive some general kinematic variables are the collider coordinate. Important to understand what means collider coordinate. We have here the coordinates atlas, for example. We can see that the collisions occur in direction of the z-axis, and the x-axis point to the center of the circle, and y a point in the normal direction, right? So the collisions occur in direction of the z-axis. So this is important. This is the collider coordinates. Important to maintain that. For example, in the LHC, after of the energy that we today, the energy of the LHC is around 13.6 GeV. But imagine that we have only 13 GeV. So imagine that we can write the force vector for the protons. So P mu is equal to the energy and the moment in x, the moment in y, and the moment, sorry, here. As I say, the actual energy of the LHC is around 13.6 GeV, but imagine that we work with only 13 GeV. So the moment of the first proton, P, first proton, is equal to energy and the components of the linear momentum. And following the collider coordinates, we don't have components or in the for the protons in the x and y momentum. So we only have energy 0, 0, and the z moment, and this is equal to 6.5 TeV. Sorry, here not GeV, TeV, and 0, 0, and 6.5 TeV, right? For the first proton, and for the second proton, the collisions are symmetry. We have the same thing. 6.5 T. So that 2 for momentum is for protons. But here occur a curiosity. For me, proton is one of the most complex things that we can find in the nature, because imagine a proton. Proton is a particle that is composed by 3 quarks, right? But exists the possibility from the quantum mechanics laws that produce that protons interact via gluons. No. But for example, exists the possibility that a gluon that has the property to itself interactions can be produced two pairs of quark-antiquark, and again produce a gluon. We can produce again two pairs of quark-antiquark, right? Another gluon with another gluon, we can produce a quark-antiquark again. So in general, proton is a very complex system, physical system. So inside of the proton, we have partons that are quarks and gluons. So they call it, that represent a problem, because Imagine the collisions between two protons, a proton here and a proton here. We have the momentum of the proton, P1 and P2, that are the linear moment, that moment that is the four moment. So we have the moments that are perfectly in the z direction, but we have here we have quarks, and the momentum of the quarks is randomly, right? That moment a point here, point here, point here, point here. So that represents a problem because the total moment of the parton system exists the possibility that point different from the linear collisions. So for example, we can find the total moment of the partons that side, for example, and here the total moment a point here. So we have two different systems of reference. So that is a problem because imagine the production of a Z boson. The Z boson is produced at rest. For example, if the parton center of mass energy, the parton of the third of a quark, for example, plus the second parton produce a Z boson at rest. But if we see that same process from the laboratory that are the or protons, exists the possibility that the production is not at rest. So we have two difference of information. So to solve that, we need to use special relativity again. Why? Do a transformation. That is the boost transformation. The boost transformation, for example, is the following metrics. The transformation are metrics in that sense. Exists the kz equal to cosine hyperbolic beta. That metrics we study in special relativity. My work is not demonstrate that. It's only show the result. Sine hyperbolic and 0 0 sine hyperbolic beta 1 0 0 0 0. That is the transformation, a boost transformation, a longitudinal boost transformation in the z direction. Beta equal to v over c, that is equal to v, using the units, natural unit. So if we have a arbitrary momentum, energy, moment in x, sorry, and y and z, and we apply that calculus in that is the same matrix with that part that apply to energy, px, py, and pz, we can show the following results that are the relation between the partons parton reference of system and the laboratory system. We have the result of A transform as cosine hyperbolic beta plus pz sine hyperbolic beta. We have another, we can demonstrate that px is maintained. Important. Py maintain again. And pz equal to pz sine hyperbolic beta plus E sine hyperbolic beta. So here we can see that appear quantities, kinematic quantities that are invariant, that has the same value in the Parton center of mass energy and in the laboratory system. So this is very important because we are these two equations, two relations are the transversal moment, are has part of the transversal momentum. So we can define a kinematic variable that is invariant under, that is the transversal momentum, Px plus Py. This is the transversal momentum, and this is a quantity that we are going to introduce in our algorithms to do the calculations. So this is important. So we have defined here the, in the case of the P is equal to Px squared plus Py. So we have the first invariant quantity that we can use to analyze the data from particle colliders. X is another based on that invariant quantity that we can define. That is the angle, that's the mutual angle, that is arctan between Px and Py. It's obviously that is again invariant under boost because we are going we use the same invariant quantity. So that angle we can analyze in from the events in particle colliders. So exists another quantity that is important to understand, that if we take that relation, we can see that if we do the transformation, we can obtain E sine hyperbolic Pz sine hyperbolic beta plus Pz hyperbolic plus E over so the step that I do here was substitute that relations that I find here. Okay, after the transformation, that equation I use in that relation. So this is the result: E hyperbolic beta plus B sine beta minus D sine hyperbolic beta minus E sine hyperbolic. So we can show that the final result of that calculus is E plus Pz over E minus times sine hyperbolic beta plus sine hyperbolic beta. So we obtain a quantity that is not invariant, but depend on this factor. How we can eliminate this factor? With a difference between that relations. If we take, for example, the logarithm plus Pz and E is equal to logarithm E plus P minus P plus the logarithm of that quantity. Sine hyperbolic beta minus sine square. So if we made some transformation, we can obtain the following equation. Logarithm minus igual a logarithm of theta minus. So that quantity don't depend on the linear momentum t. So again, we obtain a quantity that is invariant under Boost transformation, and we call that expression rapidity. That is that we use y 1/2 per. This is the quantity that we are going to use to analyze our data in a click compact linear collider. Yes. Yes. So again, as I say, that quantity, remember, that quantity is not invariant under boost transformation. The, the difference is a boost transformation. So we are going to use that quantity to analyze our events particle. Another quantity that we can use, but in this that paper I don't use, but we can use are the delta R separation that is related to the delta Y, that is a invariant quantity, minus delta P, that is another invariant quantity. So we have here again another invariant quantity. So this is the message of the lecture. We need to find invariant quantities to analyze, to do a correct analysis of the events that we can find in the particles collision. Okay. I have time for another calculus, so I okay. I can send that calculus for okay. Thank you. So some questions, easy questions. Delta R separation. Just let. Yes.
All right. So no further questions. I'm checking here. Nothing. Okay. So for those who haven't filled up please check the form. I fixed it. Go there and up your information. But easy.
What?
Okay. All right. So for the question. All right. So let's go for the next. Let's thank the Mauricio for his talk. Much Mauricio.
Those?
Now we go